All right, so now that we have like briefly explained what the token age contract does with the checkpoints and so on, and drawing it all out in diagrams, I'm going to look at the code. And the token age checkpointing abstract contract is like the base for the token age contract, and it defines a bunch of things like balances and delegates and so on. And I'm actually going to start at the very bottom of the file. So here we have those time functions, and the idea here is that we actually want to first decouple the checkpointing code from block numbers and so on, since someday we might want to use something else for time and not block number, like maybe the current vote or something like that. So a bit of future proofing. And the other thing is we want to actually convert the time to an 64-bit number, and that way we can fit it a bit more compactly in the state. So about the state. The state is a few mappings of checkpoints or stacks, depending on what we are working with. Just to remind ourselves, we had the stack of balances and token ages, which is the balance stack or the balance stacks, which is just the balance for an individual user. And we are using the balance checkpoint struct because it is actually identical to what a balance stack item would be if we were to have such a struct. Then we have the delegated balance checkpoints, which is the checkpoints for the balance, but actually we are using the delegated balance, so the total token age including the delegations, which allows for weight of add to actually use the delegated weight. And we remember that actually get weight has to return the total weight plus the delegations. And then we have the delegated checkpoints. I'm going to currently skip the add and subtract functions, or actually I'm going to go with them. Never mind that. So our first function to look at is the add function, which the diagram was noted here, like adding a new item on top of the stack, and also making sure we update the delegated balance checkpoints and the delegate checkpoints and everything else. So we take an owner and the amount of balance we want to add, like the amount of tokens, and take the stack. Again, this is a pointer. We take the last item on the stack using this get last checkpoint function, which is like a helper. We get the token age for that checkpoint at the current time, which is again something we were making note of when adding a new item on top. We just set its time to the current time, then the token age is the token age at that time. This would be like 8 by 3, 24, so that will be like 59 total, like 35 plus another 24 from the 8 balance multiplied by 3. So we record the token age and push a new stack item on top of the stack. And here again we are reusing checkpoint functions for the stack. We increase the balance, update the token age, and update the delegated call this update delegated balances, which we are going to be looking at in a moment. So I'm just going to switch to the get last checkpoints and push checkpoint functions, which are way below. So the get last checkpoint function currently has to be implemented twice because Solidity does not have generics or templates or anything like that. But each of the implementations is the same. And here the idea is that we return the checkpoint at the last index, or if there is no checkpoint in the stack, so if it's an empty stack or an empty list of checkpoints, we just return this new balance checkpoint. And actually, the new balance checkpoint is a special variable we keep around. We never write to it, and it just stays 0 the whole time. And actually, this is free in Solidity, and we're just using it in order to get a new value, or like a 0 checkpoint. And it is important to not write to the checkpoint returned by get last checkpoint, because we never want to write to the new balance checkpoint or the new delegate checkpoint. Then we have the push checkpoint function, which takes the current time, and then if the checkpoint on top is for the same time, we just return the checkpoint on top. No, this is writable. Otherwise, we push a new checkpoint and set it from time. So in the end, we always end up with this condition met. But if it's not met, we just add a new checkpoint to make it so. And we can use that in the add function for the stack, because if we are adding token in the same block twice, we actually don't want to add another stack item. So we don't want to have like another stack item for the same time, because it's absolutely useless. Like they're identical, except for the balance. And we can just reuse the same storage. So then for the subtract function, I'm just going to go without the delegation for the moment, just for the stack. Again, we take the stack, we take the last item on the stack, we calculate the new balance. Note that in Solidity 0.8, which is like, this is the reason we're using Solidity 0.8, subtraction actually throws in case there is an overflow or an underflow. So in this case, this is going to throw if there is not enough balance, because it is so unsigned integers. Then we have the last token age again, and we don't need that for the moment. Never mind. We just calculate the new balance. If it's 0, then we can directly go ahead and delete the whole balance stack. Otherwise, we go over the balance, over the stack, and while the new balance is less than or equal to the balance on top of the stack, or wait, that's not on top of the stack. Let me try to explain this. So the idea is the following. We have our stack of balances, and again, as a reminder, the token age is the token age below the stack item. Hence, we only care for the balance right now and updating the balance. So if the user wants to transfer, for example, one token from this stack, we can just decrement the balance on top, and it will still be a valid stack. Like the token age will be computed correctly afterwards. However, remove 2 tokens, and now we can drop the top item, because it's equal to the balance below it. Now, for example, if this has to become 7, then we have to drop this and update this, if that makes sense. I'm not sure if this explanation made sense, so feel free to go ahead and ask questions about it, and I'll be happy to try again. But the basic idea is to maintain the invariant that the balance on top of the stack is always more than the balance below it, because otherwise this would correspond to a negative amount in the previous version of the stack, like the one with the amounts. So we pop items from the stack until the top item can be edited freely, and then we just edit that. And here there is a note that we know that the stack length is more than 0, because if it was 0, then get last checkpoint would return the new checkpoint, and then this balance would be 0, so this will directly throw, or this would be 0. So then we take the new token age at the end, recomputing the last checkpoint on the stack, because actually this variable is now stale, because we have changed the stack, and perhaps we have actually popped that element. And we just take the token age from the new last checkpoint at the current time, and we use that for updating delegated balances. But again, more on that later. So this is the add and subtract functions. They basically manipulate the stack, and at the end just go update delegated balances in order to update the checkpoints. And I'm actually just like for a brief pause before I dive into the update delegated balances function, just to review the get token age function real quick. Basically takes a checkpoint, like the checkpoint from which we are computing the token age or the stack item, and then the block at which we want it calculated, and we just take the token age of the checkpoint. So that is the token age before that checkpoint, like at the start. Then we add the balance multiplied by the difference in the time. So all of those tokens are gaining a new token age, or new weight for that many blocks. Right. Just going back, the next function on the list is the update delegated balances, which takes the delegate or the person we want to update the delegated balances for. Then we take the change in the balance. Here we're using a signed integer in order to not have a Boolean flag and then an if-else for that integer. I think it's a bit faster that way. And finally we have the token age change, which is like the balance change, but like how much the token age has changed in that. So for example, when we add a new item in the stack, when we add some more tokens to the user, then we have a balance difference, like we have new tokens, but we don't have a token age difference because the token age actually stays the same. But when we subtract tokens, then we have a balance difference, and we also have a token age change because the user has lost some token age in the operation. And again, just to go to the diagram, when we were transferring a token, the user actually lost a bit of weight through that transfer. So if the token has some kind of weight, I think it was 7 here, it actually gets destroyed and becomes like weight 0 because of the transfer. And hence there is a weight change when we're subtracting balances. And update delegated balances would iterate over all the delegates in the chain. And just to illustrate that real quick, the idea with delegates is that we have a few addresses, like A, who is delegating to B, who is delegating to C. And it kind of forms like a tree because everyone can delegate to one address. So maybe there are multiple addresses delegating to B. And the idea is that even though they're delegating, when they transfer, they still lose token weight or token age. The delegation is only for voting, it's not for the token age calculation. So what we do is we go from the current, for the owner whose balance was changed, and we go up the tree of delegates. Like we get the current delegate we're iterating, we iterate it until its address 0, and we just get the last checkpoint for the delegate. So we just get the current delegate for that address, and we have a quick check that we're not in a cycle. Actually, I'm thinking this check might actually be broken. Though no, wait. Actually, it's not broken because you cannot create a cycle because of it. Yeah, just to explain that, when you do a set delegate call, which is actually updating the delegate, it calls update delegated balances. So if you try to create a cycle, like say C tries to start delegating to B, then this call will error out because we're going to get back to C, no matter where we go. If it's creating a cycle, it will get back to C at some point, or to whoever is creating the cycle. Anyway, so we iterate the delegates up the delegate tree, and for each of the delegates, we take the current balance checkpoints, like the balance checkpoints of that delegate. So for example, for address A, let's say, we're taking the checkpoints, and then we take the last checkpoint, we compute the new token age for that checkpoint, and actually that new token age is going to be for the current time. So we get the token age of that checkpoint. We add the change in token age. So that's why it was, for example, 0 here, because we are going to be taking the current one and adding no change to it because we are adding tokens and they don't change the token age immediately. Guess I got a little bit lost there. But we compute the new token age. And actually we can compute the new balance as well, but I'm doing it directly. But at any rate, we create a new checkpoint for that checkpoint stack, or list more like. We push a new checkpoint, and then we update its balance to be like the old balance plus the balance change, and the token age to be the new token age we just computed. And finally, we update the iterator, make sure we're not making a cycle, and loop until we're at address 0. And that way we are actually keeping the total delegated token age and balance computed for a given. Pretty sure the math checks out here. But basically the idea is that, let's say we have some balance, like 3 and the token age at the current moment of computing everything. Like, let's say it's also 3 here. Let's say address D has a balance of just 1 coin, but has a token age of, say, 10 because it held that coin for a longer period of time. Then we have address B balance. Let's see, B actually also has a balance, like a 5. And token age for that 5, so that's not the delegated token age, that's B's own token age of, say, 15. And address C maybe has a balance of 0 and a token age of 0. This is like before the delegations are computed. So we then compute the delegated token ages and balances. I'm just going to write them in the same place, just with the... So the delegated balance is also 1 and the delegated token age is also 10 because nobody is delegating to D. More like I can actually... No, I'm just going to keep going. So here we have 5 balance from B and also 3 and 1 from A and D. So that's 4 and 5, 9. And for the token age we have 13 from the delegation, so we have a total of 28. And for C we just have those same numbers because C adds no balance or token age. So the idea here is that when we are updating the balance, so actually, just a second. So actually each of those also has a from time in the checkpoints and on the stacks. So we have a from time, for example, this is from block 5. So now at any time we can compute the delegated token age to any address by just looking at the top delegated checkpoint and computing the token age from there. So for example, if you want to compute the token age for address A at time 7, then we have that the token age equals, like the delegated token age would be like 3, which we have like recorded in the delegated checkpoint, plus 3 for the balance multiplied by the difference in time. So that would be like 9. And similarly, for example, for address C at time 7, the delegated token age would be 28 plus 9 multiplied by 2. And if at that time 7 we actually want to decrease, let's say, address A's balance, so let's say that we are making an operation that leaves address A with 1 balance, so the change in balance is like -2, and the token age change would be, actually we first compute the like the new token age after the change. So this is going to get a bit odd because we don't have the previous checkpoint like written on the diagram. But let's say that the token age goes down by -4, just for an example. So when we change the balance, it becomes 1, and delegated balance is also 1, and the token age becomes so that goes to the lower checkpoint, actually, lower item on the stack. So maybe token age actually becomes 0, and we are now from time, let's say 2, or actually the from time does not matter if token age is 0. Let's say we go to 0, yeah, or maybe we actually go to 7. Never mind that. I got confused there. Sorry about that. Actually, the difference in token age in this case would be, no, that's not 7, so that's 5. Is it 5? No. Okay, let's just arbitrarily set this to 3. Sorry. So like there was a stack on which there was like one token received at time 3 and then two more tokens received at time 5. If that makes some sense. At any rate, like we had the delegated time token age calculated before the change, and after the change, actually that's not the delegated, that's the non-delegated token age. Let's see. So after the change, our not delegated token age is 1, so 0 plus 1 multiplied by the difference in times, so just 4. Actually, the difference in token age becomes 5. My bad. Yep. Now that we know the difference in balance and the difference in token age, we start updating the delegated token age using the same numbers. So let me just... I have messed something up. No, I have not. Okay, so the delegated checkpoints at this point in the program execution actually have from time 5. I guess this makes little sense when I track it like that. I probably have to try to re-record this part. We go ahead and start computing with the balance and token age changes. And currently the from time has to be set at 7, since those are the checkpoints and we want to have the from time always current time. We cannot like go back in time with the checkpoints. We compute the token age at this time, it was 9, and we then apply the token age change, so this becomes a 4, and the balance change. And actually, here on, we can see that actually the delegated token age and the non-delegated token age is still the same, because we just have this addition of 4 instead of 1 multiplied by 4. And then we propagate this change up the tree of delegates. So we take the delegated token age as computed before. So actually I will have to compute that, but that is 36, I think. So we reduce the balance by the difference in the balance. The token age should be 46 if there was no change, but there is a change, so it becomes 41. And we go similarly for the address C. And I guess this might be a bit confusing. It took a while to wrap around in my head. Sorry for taking all that time on recording. And I can probably try to explain it again if it not makes much sense. Basic idea is that the checkpoints always have to be like for the latest checkpoint, for the latest time, and we only add new checkpoints on top. We never modify or pop checkpoints, while the stacks can be modified, and we actually regularly modify the stack. For example, when we subtract tokens, we go to the top stack item and just reduce its balance. So that was about delegated balances and updates function. Just as a quick recap, it iterates over the delegates, takes the balance checkpoints for the current delegate, like the current person we're recomputing the balance of. We take the last checkpoint, we get the last token age, and we add the change in token age. And we are going through some casting here to get those signed integers to work with the unsigned integers used elsewhere. Then we do something like that with the balance. And currently we are making use of the fact that push checkpoint never invalidates the last checkpoint. Otherwise, we might just have to move this into a variable above the push checkpoint call. And we also update the token age, and we continue iterating up. And most of the magic actually happens with this get token age call here. Like most of the reason I was a bit confused while explaining it down here. And finally, I think, no, we actually have a few more functions, but we have this set delegate function, which updates the delegate for a given address. And to do that, it gets the last delegated checkpoint for that address. It takes its current balance and token age. It gets its out delegate, like that's the balance and token age it is currently delegating to someone else. It gets its current delegate, updates the delegated balances of that current delegate to subtract its own contribution to the delegate, and then updates the delegate, and finally delegates its balances and token age to it. So to go back here, if say address A starts delegating to some new address we just what would happen then is we would take the current balance and token age it is delegating. Let's say it is happening at time 9. So at time 9, the delegated token age by address A would be 4 plus 1 multiplied by 9 by 5 minus 5, which is 6. So it stops delegating 1 balance and 6 token age. And actually, so we go here and we recompute the delegated token age for address B. So time 9, it has 41 plus 7 multiplied by 2, so 55, I think. And we subtract those 6 from them. So this becomes a 49 at time 9. And we do exactly the same computation for address C. And then, after we have removed the contribution from address A to those addresses, we update it to point to the new delegate, and we add that token age and balance that address A is delegating. And that's how set delegate works. It basically gets the old delegate, propagates the fact that we are no longer delegating to him or to it, and then it gets the new delegate and starts delegating to that delegate. And those are the messy functions. So those are the state changing functions that token age checkpointing defines. And finally, we have the get checkpoint binary search. Like when we have those checkpoints, when we want to get the weight at a different at a given block height or block number, we actually use get checkpoint at that time. And for that, we first check if this is a binary search from kind of adapted from Wikipedia, we have to admit. So if we have no stack or the start time is before the first checkpoint on the stack, we return. Or if we're after the end of the stack, like after the top, we return the top element. Otherwise, we make a binary search, taking the middle element with the floor between the start and the end element, floor we have. And if the midpoint, if the checkpoint at that middle element is after the time, we update the end, otherwise the start. And this might need some careful double checking. Experimentally, it works and it should be the right algorithm, but as there are a few variations of the binary search algorithm, you might want to double check that. Basically, the idea is to return the checkpoint before that time. So for example, if somebody asks for time like say 18, we want this checkpoint, the one for 17. Or if somebody asks for time 17, we again want the checkpoint for time 17. But at the moment somebody asks for time 16, we want the checkpoint for time 10. And that's it. We have made it past the token age checkpointing